quiet night, anywhere on Earth. You look up and see a scattering of stars, faint pinpricks against the dark. The sky seems still, unchanging, as if the universe has always been this way and always will be. But far beyond anything your eye can see, far beyond the reach of even the most powerful backyard telescope, something extraordinary is happening. 8 to 9 billion light-years away, a black hole weighing tens of millions of times more than our sun is racing through space at nearly 1,000,000 miles per hour, leaving behind it a glowing trail of newborn stars that stretches twice the width of our entire galaxy. This is not a story of destruction or catastrophe. It is a story of motion, of gravity's surprising consequences, and of how patient observation can finally confirm ideas that lived for decades only in equations and simulations. It is the story of a runaway heart, a supermassive black hole that broke free from its home galaxy and now wanders the space between worlds, writing its own luminous signature across the cosmos. For most of the history of astronomy, scientists believed that the massive black holes at the centres of galaxies were essentially fixed in place. Every large galaxy, as far as we could tell, had a supermassive black hole at its core, a gravitational anchor millions or billions of times the mass of the Sun. These objects shape the orbits of stars around them, heat the gas that spirals inward, and sometimes power brilliant jets of radiation that blaze across intergalactic space. They are the hearts of galaxies, and for a long time we assumed those hearts stayed put. Galaxies might collide, merge, and reshape themselves over hundreds of millions of years, but their central black holes would eventually settle down together at the new centre of mass, locked in place by the combined gravity of billions of stars. The idea that one of these enormous objects could be kicked out entirely, sent careening into the void like a stone from a slingshot, seemed plausible in theory, but difficult to prove. And then, in December 2025, astronomers announced that they had done exactly that. Using the James Webb Space Telescope, they confirmed the first clear example of a runaway supermassive black hole, a galactic heart torn from its home and set loose in the space between galaxies. The setting for this discovery is a strange and beautiful pair of galaxies whose light has travelled across most of the age of the universe to reach us. When astronomers first imaged this system with space telescopes like Hubble and later JWST, they noticed something striking. The two galaxies appeared as overlapping rings, their circular arcs of stars and gas arranged in a pattern that looked, to some observers, like a pair of wide, staring eyes. Someone nicknamed the system the Cosmic Owl, and the name stuck. Others called it the Infinity Galaxy, because when viewed from certain angles the overlapping rings resembled the symbol for infinity, that looping figure 8 that mathematicians use to represent endlessness. Both names capture something of the system's character, a sense of looking back at us across the gulf of space and time, a sense of cycles and loops and connections that stretch beyond easy comprehension. Ring galaxies are not common, but they are not entirely rare either. They form when one galaxy passes through another, triggering a ripple of star formation that expands outward in a circular wave, like the ripples on a pond when you toss in a stone. Over tens or hundreds of millions of years, these ripples can produce distinct rings of bright young stars, tracing the path of the disturbance through the gas and dust of the colliding galaxies. The Cosmic Owl is a particularly dramatic example, with two prominent rings that overlap and interact, evidence of a complex gravitational dance between multiple galaxies. When we look at this system, we are seeing it as it was 8 to 9 billion years ago, when the universe was less than half its current age. The light that reaches our telescopes left the Cosmic Owl long before our Sun or Earth existed, carrying with it a frozen snapshot of a collision that unfolded over timescales far longer than any human lifetime. And it was in this ancient, distant system that astronomers noticed something odd. A long, straight streak of light, stretching along one side of the Cosmic Owl like a scratch across a photograph. The feature was thin and linear, running for roughly 200,000 light-years, about twice the diameter of the Milky Way. It was unlike the curved arcs and rings produced by normal galaxy collisions. It looked, in fact, more like a wake, the kind of trail you might see behind a boat moving through water or a jet moving through the sky, leaving a contrail of condensed vapour in its path. But this was not water or air. This was the thin, diffuse gas that fills the space between and within galaxies, and something had ploughed through it with enough speed and mass to compress that gas, shock it, and trigger the birth of new stars all along a narrow ruler-straight line. For years, this feature was a puzzle. Early observations suggested it might be evidence of something moving through the gas, but what? The most exciting possibility was a runaway supermassive black hole, an object so massive that its passage would disturb the surrounding medium, creating a bow shock at its leading edge and leaving behind a wake of compressed gas where stars could form. But other explanations were possible. Perhaps it was just an unusual stream of gas, shaped by tidal forces during the galaxy collision. Perhaps it was a misidentified arm of one of the ring galaxies, stretched out by rotation or gravitational torques. Astronomers debated the possibilities, but without more detailed data, the streak remained ambiguous, a tantalizing hint without a definitive answer. To understand what makes this discovery so significant, it helps to step back and consider what a supermassive black hole actually is. Black holes come in different sizes. The smallest are stellar mass black holes, the remnants of massive stars that have exhausted their nuclear fuel and collapsed under their own gravity. These objects typically weigh anywhere from a few times the mass of the Sun, up to perhaps a few dozen solar masses. They form in supernova explosions, the violent deaths of stars, and they are scattered throughout galaxies wherever massive stars have lived and died. But supermassive black holes are a different beast entirely. They weigh millions or even billions of times the mass of the Sun, and they reside not in the scattered debris of stellar explosions, but at the very centres of galaxies, where they exert a profound influence on everything around them. How supermassive black holes form is still a matter of active research, but we know they must have grown over billions of years by swallowing gas, dust, and occasionally entire stars, and by merging with other black holes during galaxy collisions. The gravity near a supermassive black hole is so intense that it warps space and time itself, bending the paths of light and matter in ways that can only be described using Einstein's general relativity. Material that falls towards such an object doesn't just disappear quietly. It forms a swirling disk, an accretion disk, where friction and magnetic fields heat the gas to millions of degrees, causing it to glow brightly across the electromagnetic spectrum. Some supermassive black holes are surrounded by these brilliant disks, which can outshine entire galaxies, while others are quieter, lurking in darkness with only the motion of nearby stars to betray their presence. Astronomers infer the existence of supermassive black holes, not by seeing them directly. After all, the black hole itself emits no light, but by watching how matter and light behave in their vicinity. Stars near the centre of the Milky Way, for example, have been tracked for decades as they orbit an invisible point at speeds that reach a significant fraction of the speed of light. The only explanation for such rapid motion is the presence of a black hole weighing about 4 million times the mass of the Sun, sitting right at the galactic centre. Similar measurements in other galaxies reveal similar central black holes. Their mass is correlated with the overall mass of the galaxy's central bulge. It seems that galaxies and their central black holes grow together, feeding off the same supply of gas and stars, locked in a relationship that shapes both over cosmic time. Given how massive these objects are, and how central they are to the structure of galaxies, it might seem impossible for them to go anywhere. The combined gravity of billions of stars should hold a supermassive black hole firmly in place, the way the Sun holds the planets in their orbits. And indeed, under normal circumstances, that's exactly what happens. A supermassive black hole at the centre of a quiet, isolated galaxy will stay put, anchored by the gravitational potential well created by all the surrounding matter. But galaxies are not always quiet and isolated. They collide, they merge, and when they do, their central black holes are drawn together, spiralling inward over hundreds of millions of years until they meet at the centre of the newly merged galaxy. And it is in these violent, chaotic encounters that the rare and surprising phenomenon of a runaway black hole can occur. The idea that supermassive black holes could be ejected from galaxies is not new. Theorists have been predicting it for decades, working out the physics in computer simulations and mathematical models. Two main mechanisms have been proposed, both of which rely on the complex gravitational interactions that happen when galaxies merge. The first is what's sometimes called a three-body slingshot. Imagine not two but three supermassive black holes interacting in the same galactic centre. This can happen when multiple galaxies merge in quick succession. or when a galaxy that has already undergone one merger collides with another before its two central black holes have had time to settle down. In such a scenario, the three black holes orbit each other in a chaotic dance, their mutual gravitational pulls tugging and yanking in ways that can become unstable. Under the right circumstances, one of the black holes can be flung outward, gaining enough speed to escape the gravitational pull of the galaxy entirely. It's a cosmic version of the slingshot effect that space missions use to gain speed by swinging past planets. Except here, there are no careful trajectories or planned burns, just the raw, chaotic dynamics of three enormous masses interacting in close quarters. The second mechanism is gravitational wave recoil. When two supermassive black holes spiral together and finally merge, they don't just combine their masses, they emit gravitational waves, ripples in the fabric of space-time itself, travelling outward at the speed of light and carrying away energy and momentum. If those gravitational waves are emitted symmetrically in all directions, the merged black hole stays put, its centre of mass unchanged. But if the waves are stronger in one direction than another, which can happen if the two original black holes have different masses, or if they are spinning in certain ways, the merged black hole will recoil, kicked in the opposite direction, like a gun recoiling when it fires a bullet. The amount of kick depends on the details of the merger, but simulations suggest it can be substantial, potentially reaching speeds of thousands of kilometers per second, more than enough to escape even a massive galaxy's gravitational pull. For a long time, these ideas remained largely theoretical. Astronomers suspected that runaway supermassive black holes should exist somewhere out there in the universe, wandering the space between galaxies or moving through galactic halos far from their original homes. But finding them was another matter. A black hole on its own emits no light, and even a supermassive one, millions of times the mass of the Sun, is effectively invisible against the vast backdrop of space. To detect a runaway black hole, astronomers would need to catch it in the act of interacting with something, ploughing through gas, for example, or dragging along a disk of accreting material that glows as it heats up. Even then, distinguishing a runaway black hole from other astrophysical phenomena would require careful measurements of motion, mass, and the surrounding environment. It was a needle in a haystack problem, and for decades, the needles remained hidden. The cosmic owl changed that, when the James Webb Space Telescope turned its powerful infrared instruments toward the tip of that long, puzzling streak of light. It was able to do something earlier telescopes could not: measure in exquisite detail how the gas in that region was moving and how its light was shifted by motion and heating. JWST's ENIA-SPEC integral field spectrograph is a remarkable piece of technology. It doesn't just take a picture or capture a spectrum of a single point. It divides a small patch of sky into thousands of tiny regions, obtaining a complete spectrum for each one, mapping out the velocity, temperature, and chemical composition of the gas across the entire area. This kind of data is extraordinarily rich, and in the case of the cosmic owl, it revealed something unmistakable. At the tip of the linear feature, the gas showed a sharp change in velocity, about 600 kilometers per second across a region only about 1 kiloparsec wide, roughly 3,200 light-years. That's a dramatic shift, far too abrupt to be explained by normal galactic rotation or the gentle flows of gas in a merging system. The data suggested that the gas was being shocked, compressed by something moving through it faster than the speed of sound in that medium. When an object moves through a fluid faster than sound waves can travel in that fluid, it creates a shock wave, a sudden jump in pressure and temperature as the fluid piles up ahead of the moving object. We see this on Earth when a jet breaks the sound barrier, creating a sonic boom. In space, the same physics applies to objects moving through the thin gas that fills galaxies and the space between them. By modelling the observed velocity shifts and the structure of the shock, the astronomers who analysed the JWST data were able to infer the properties of the object creating it. The black hole itself, they concluded, was moving at roughly 950 to 1,000 kilometers per second, around 2.2 million miles per hour. That's fast enough to cross the distance from Earth to the Moon in about 6 minutes. The mass, based on the strength of the shock and the dynamics of the surrounding gas, was estimated at a minimum of 10 million times the mass of the Sun, possibly more. These numbers fit perfectly with what you would expect from a runaway supermassive black hole. Massive enough to plough through the intergalactic medium without being deflected, fast enough to escape the gravitational pull of its home galaxy, and creating a bow shock at its leading edge where gas is compressed and heated. This was the confirmation astronomers had been waiting for. The combination of high speed, large mass, and a clear bow shock signature matched the predictions from simulations and theory. The long linear feature wasn't just a stream of gas shaped by tidal forces, it was the wake of a runaway supermassive black hole, the first such object to be unambiguously identified and studied in detail. The JWST observations turned a decades-old hypothesis into a confirmed reality, giving scientists their first solid example of a galactic heart torn loose and set adrift. And that wake, that long straight trail of light, turned out to be even more interesting than just a signature of motion. When astronomers examined it more closely, they found that it wasn't just compressed gas. It was a stellar nursery, a thin string of star-forming regions stretching across 200,000 light-years. The gas compressed by the black hole's bow shock had cooled and collapsed under its own gravity, fragmenting into dense clumps where new stars were being born. Observations showed that these stars were young and blue, their intense ultraviolet light ionizing the surrounding gas and making it glow. The wake was, in effect, a galaxy-scale contrail, a visible record of the black hole's passage written in the light of newborn suns. Imagine it, a supermassive black hole, invisible itself, but leaving behind a glowing thread of stars like breadcrumbs dropped along a path. The stars farther back in the trail formed earlier, closer to the moment when the black hole was first ejected from its home. The stars near the tip formed more recently, as the black hole continued its journey and compressed fresh gas in its path. The wake is a timeline, a natural record of the black hole's motion over millions of years. By measuring the length of the trail, the ages of the stars within it, and the speed of the black hole, astronomers can estimate how long ago the ejection event occurred. The wake becomes a kind of cosmic clock, ticking off the passage of time in units of light years and stellar lifetimes. This is one of the most poetic aspects of the discovery. In astronomy, we're used to the idea that light carries information about the past. Every photon that reaches our telescopes is a messenger from another time, showing us the universe as it once was. But the runaway black hole's wake takes this a step further. It is not just a frozen snapshot, but a dynamic record, a trail that shows change and motion over time, preserved in the luminous aftermath of the black hole's passage. It is a story written in starlight, and we are only beginning to read it. But what caused this ejection in the first place? Why is there a supermassive black hole racing through the cosmic owl instead of sitting quietly at the centre of one of its galaxies? The answer almost certainly lies in the violent gravitational interactions that occur during galaxy mergers. The cosmic owl, remember, is not a single galaxy but a pair of ring galaxies, clearly in the process of colliding and interacting. When galaxies merge, their central black holes are drawn together, spiralling inward as dynamical friction, interactions with stars and gas, drains away their orbital energy. Eventually the two black holes come close enough that their mutual gravitational attraction dominates, and they enter a tight binary orbit. If left alone, such a binary would slowly lose energy by emitting gravitational waves, eventually merging into a single, more massive black hole. But if a third black hole enters the picture before that merger happens, perhaps brought in by another galaxy colliding with the system, the dynamics change. The three-body problem in physics is notoriously chaotic, with outcomes that depend sensitively on the exact starting conditions. In simulations of triple black hole systems, researchers have found that one black hole is often ejected at high speed, while the other two remain bound and eventually merge. The ejected black hole carries away momentum and energy, a consequence of the complex gravitational interplay among the three objects. This is the three-body slingshot scenario, and it is one plausible explanation for the runaway black hole in the cosmic owl. The other possibility is gravitational wave recoil. If two of the central black holes in the cosmic owl system had already merged, and if that merger was asymmetric enough to produce a strong recoil kick, the resulting merged black hole could have been flung out of the galactic centre. The key is asymmetry. If the two original black holes had different masses, or if they were spinning in certain configurations, the gravitational waves emitted during the merger would be stronger in some directions than others, and the merged black hole would rocket away in the opposite direction. Simulations have shown that recoil velocities can reach several thousand kilometers per second in the most extreme cases, though typical kicks are smaller. The observed velocity of roughly 1,000 km per second is well within the range of what gravitational wave recoil can produce. making this a viable explanation as well. The truth is, we don't yet know for certain which mechanism is responsible. Both are consistent with the observations, and both are consistent with the chaotic, violent environment of a merging galaxy system like the cosmic owl. What we do know is that the black hole has been kicked out, that it is moving at high speed through the gas surrounding the galaxies, and that it is leaving a trail of star formation in its wake. The discovery doesn't just confirm that runaway black holes exist, it also provides a natural laboratory for studying the processes that can eject them, the way they interact with their environment, and the consequences of their motion over millions of years. One of the most exciting implications of this discovery is that it gives astronomers a new way to search for similar objects. If runaway supermassive black holes produce long linear wakes of star formation, then finding more of them may be a matter of looking for these distinctive trails in deep surveys of the sky. The James Webb Space Telescope is now observing the universe in unprecedented detail, mapping distant galaxies and their surroundings with a sensitivity that earlier telescopes could not match. Upcoming missions like the Euclid Space Telescope and NASA's Nancy Grace Roman Space Telescope will survey even larger areas, building up vast catalogues of galaxies across cosmic time. If other runaway black holes are out there producing similar wakes, these surveys should be able to find them, and finding more examples would be scientifically invaluable. Each runaway black hole is a test case for the theories of black hole mergers and ejections. By measuring their speeds, masses, and the properties of their wakes, astronomers can refine their models of how galaxies and their central black holes evolve over time. They can estimate how often these ejections happen, what fraction of galaxies might have lost their central black holes, and how this affects the growth and structure of galaxies over billions of years. A single example is remarkable, but a population of runaway black holes would open up an entirely new window into the dynamics of galaxy mergers and the fate of the supermassive black holes at their centres. The discovery also changes the mental picture we have of galaxies and their evolution. For decades, the standard model has been that every large galaxy has a supermassive black hole at its centre, and that these black holes grow steadily over time through accretion and mergers. When two galaxies merge, their central black holes merge as well, settling into a new equilibrium at the centre of the combined system. This picture is mostly correct, but the cosmic owl shows that it is not the whole story. In rare cases, a galaxy can lose its central black hole entirely, ejected into the surrounding halo, or even into intergalactic space. The galaxy is left without its heart, at least temporarily. Over time, it may regrow a new central black hole by accreting gas and capturing smaller black holes from its surroundings, but the original has been lost, wandering alone through the cosmos. This adds a layer of complexity and unpredictability to the story of galaxy evolution. Galaxies are not just growing and merging in orderly, predictable ways. They are sometimes losing their most massive central objects, redistributing matter and energy across vast distances, reshaping themselves in response to rare but dramatic events. The universe, it turns out, is not only expanding but also rearranging its contents in subtle, sometimes unexpected ways. Supermassive black holes, once thought to be permanent fixtures at galactic centres, can sometimes break free, leaving behind only a faint trail of stars to mark their passage. There is something quietly profound about this. We're used to thinking of astronomical objects as fixed in their roles. Stars orbit galaxies, galaxies orbit galaxy clusters, black holes sit at the centres of galaxies. But the universe is more fluid than that. Even the heaviest, most massive objects can be moved, can be displaced, can wander. The runaway black hole in the cosmic owl is a reminder that gravity, for all its power, is not always a force of stability. It can also be a force of disruption, capable of flinging even supermassive objects across space, writing new patterns in the distribution of matter and light. The runaway black hole also serves as a kind of natural experiment, revealing aspects of black hole physics and galactic dynamics that are hard to study in any other way. By observing the bow shock at the black hole's leading edge, astronomers can learn about the properties of the intergalactic medium, its density, temperature, and composition. By studying the wake, they can learn about star formation triggered by shocks, a process that may have been important in the early universe when galaxies were first forming and gas was being compressed by collisions and cosmic flows. The runaway black hole is, in effect, a moving laboratory, probing its environment as it travels and leaving behind a record that we can observe and analyse. And it is worth emphasising again that this discovery did not come from a single observation or a single telescope. It is the result of decades of work, building up the technology and the theoretical framework needed to identify and confirm such an object. Early images from Hubble revealed the cosmic owl and its strange linear feature, sparking curiosity and debate. Ground-based telescopes contributed follow-up observations, measuring the light from the streak and hinting at the presence of young stars. Theoretical work provided the context, predicting that runaway black holes should exist and outlining what their signatures might look like. And finally, JWST delivered the detailed spectroscopic data that clinched the case, showing the bow shock and allowing astronomers to measure the black hole's speed and mass with confidence. It is a perfect example of how modern astronomy works: incremental progress, careful observation, and the patient accumulation of evidence over many years, leading at last to a moment of clarity and confirmation. The discovery was announced in December 2025 after rigorous analysis and peer review, and it was met with excitement across the astronomical community. Here, at last, was the first unambiguous example of a runaway supermassive black hole, the confirmation of a phenomenon that had been theorized for decades but never clearly observed. The papers describing the work were posted to the Archive preprint server and published in leading journals, where other scientists could read the details and begin planning follow-up studies. News of the discovery spread through press releases and science journalism, bringing the story to a wider audience. People like you looking up at the night sky and wondering about the hidden motions and dramas unfolding far beyond the reach of human eyes. But for all the excitement, there is also a sense of calm and perspective that comes with this kind of discovery. The runaway black hole in the cosmic owl is not a threat. It is not hurtling toward us, and even if it were, the vast distances involved mean it would take billions of years to cross the space between its galaxy and ours. It is simply there, doing what physics dictates it must do, moving through space, interacting with the gas around it, creating a wake of stars. It does not know we are watching. It does not care. It is a consequence of gravity and motion, playing out on scales that dwarf human concerns, and yet it teaches us something fundamental about the universe we inhabit. It teaches us that even the heaviest objects can be moved. It teaches us that galaxies are not static, eternal structures, but dynamic systems shaped by collisions, mergers, and rare, violent events. It teaches us that patient observation, careful measurement, and the steady accumulation of knowledge can eventually reveal phenomena that once seemed impossible to detect. And it teaches us humility, a reminder that for all we have learned, the universe still holds surprises, still offers up new wonders for those willing to look closely and think deeply about what they see. As you stand under the night sky, or lie in bed thinking about the distant cosmos, it is worth holding that thought. The stars above you are part of a galaxy that, as far as we know, has a supermassive black hole quietly sitting at its centre, holding everything in a delicate gravitational balance. But somewhere out there, in a galaxy system called the Cosmic Owl, a black hole that once held a similar position has broken free, racing through space at nearly 1 million miles per hour, trailing stars in its wake like sparks from a fire. It is a rare event, a cosmic oddity, but it is real, and it is happening right now. Or rather, it was happening 8 to 9 billion years ago, and the light from it is reaching us only now, carrying the news across the vast gulf of space and time. This is the nature of astronomy. We're always looking backward, seeing things not as they are but as they were. The runaway black hole we observe today may have long since slowed, captured by the gravity of another galaxy, or it may still be moving, racing through ever more rarefied gas in the intergalactic void. We cannot know without waiting billions of years for new light to arrive, and of course we will not be here to see it. But that does not diminish the wonder of what we can see now. The wake is there, a 200,000 light-year thread of stars stitched across the fabric of space, a signature written in light and time, waiting for us to notice and understand, and understanding it has required the best tools and minds that humanity can bring to bear. The James Webb Space Telescope, launched after decades of planning and engineering, is one of the most sophisticated instruments ever built, capable of detecting the faint infrared glow of distant galaxies and breaking that light down into spectra that reveal the motion and composition of gas across cosmic distances. The scientists who analyse the data, astronomers, astrophysicists, specialists in black hole dynamics and galaxy evolution, brought years of training and experience to the task, piecing together evidence from multiple observations, building models, running simulations and testing hypotheses until the picture became clear. The discovery is a triumph of human curiosity and ingenuity, a reminder that we are capable of understanding things far removed from our everyday experience, as long as we're willing to look carefully and think rigorously. But it is also a reminder of how much we still do not know. The runaway black hole in the cosmic owl is the first confirmed example, but is it typical? Are there many others out there, or is this an exceptionally rare event? How often do supermassive black holes get ejected during galaxy mergers, and what determines whether they are recaptured or escape entirely? How do galaxies evolve after losing their central black holes, and how long does it take for a new one to form? These are questions that the discovery raises but does not fully answer. They will require more observations, more data, and more time to address. The work has only just begun. In the meantime, the runaway black hole continues its journey, unaware of the attention it has attracted. It does not know that its wake has been measured, its speed calculated, its mass estimated. It does not know that it has become famous, in a small and academic way, among the community of astronomers who study such things. It simply moves, as it has been moving for millions of years, compressing gas, triggering star formation, leaving behind a trail that glows softly in the infrared, a beacon that says, something passed this way. And perhaps that is the best way to think about it, not as a violent or dramatic event, but as a quiet signature, a gentle reminder that the universe is full of motion. Galaxies drift through space, stars orbit their centres, planets spin on their axes, and sometimes, very rarely, a supermassive black hole breaks free and wanders, writing its own story across the dark. The story is not one of danger or destruction. It is a story of change, of rare events that reshape the cosmos in subtle ways, of trails left behind that tell us, if we are patient enough to read them, something about how the universe works. The light from the cosmic owl has travelled for 8 to 9 billion years to reach us, crossing distances so vast that they defy easy comprehension. Along the way, the universe has expanded, carrying galaxies apart, stretching the wavelengths of light and shifting it toward the red end of the spectrum. By the time that light enters our telescopes, it has been transformed, its original blue and ultraviolet photons now glowing in the infrared, a warm, invisible glow that only instruments like JWST can detect. But the information is still there, encoded in the light spectrum, in the shifts and patterns that reveal motion, temperature, density. The light carries a message across the ages, and we have finally learned how to read it. And what it tells us is this, that in a distant galaxy system shaped like an owl or an infinity symbol, a supermassive black hole has broken free, leaving behind a trail of stars that stretches across space. The trail is a record of motion, a timeline written in starlight, a natural experiment in black hole physics and star formation. It is confirmation of a phenomenon predicted decades ago, a turning point in our understanding of how galaxies and their central black holes evolve. It is a discovery that will reshape textbooks and simulations, that will inspire new searches and new observations, that will deepen our knowledge of the cosmos in ways we cannot yet fully predict. But it is also, simply, a beautiful and strange fact about the universe we live in. There is a black hole out there, racing through space, trailing stars. It exists, it is real, and now we know about it. That knowledge does not change our daily lives. The stars above us still look the same, the moon still rises and sets, the earth still spins on its axis. But somewhere in the back of your mind, as you look up at the night sky, you can hold the thought, out there, far beyond the reach of the eye, a runaway heart is moving through the dark and we have seen its wake. This is the quiet satisfaction of astronomy, the accumulation of knowledge about things that do not touch us directly, but which enrich our understanding of the universe and our place in it. We will never visit the cosmic owl, never see the runaway black hole up close, never walk among the stars in its wake. The distances are too great, the timescales too long, the technology too far beyond our current reach. But we can observe, We can measure, we can think and calculate and understand. We can add this discovery to the growing catalogue of things we know about the universe, and we can use it to refine our theories, to test our models, to guide our future observations. And perhaps, in some distant future, when our descendants look back at the early 21st century, they will remember this as one of the moments when our picture of the cosmos shifted, when we realised that galaxies are not as stable and permanent as we once thought, when we confirmed that even supermassive black holes can be displaced and set wandering, when we began to appreciate the full dynamism and fluidity of the universe on the larger scales. They will look at the data from JST, at the images of the cosmic owl and its glowing wake, and they will see it as we see Galileo's sketches of Jupiter's moons or Hubble's plots of galaxy redshifts, a key piece of evidence that opened a new chapter in our understanding. For now, though, we are living in the moment of discovery, and there is a particular pleasure in that. The papers are fresh, the data newly analysed, the implications still being worked out. Scientists are already planning follow-up observations, searching for other runaway black holes, developing new techniques to identify them in the vast surveys of the sky. Theorists are revisiting their simulations, tweaking parameters, exploring the range of possible ejection mechanisms and the likelihood of each. The discovery has sparked a flurry of activity, a burst of excitement and curiosity that will sustain research in this area for years to come. But the black hole itself, of course, knows none of this. It does not know that it's the first of its kind to be clearly identified, that it has vindicated decades of theoretical predictions, that it has become a subject of intense scientific interest. It simply continues on its path, moving through the gas of the cosmic owl, compressing and heating it, leaving behind a trail of newborn stars. In a few million years, the wake may fade, the stars dispersing or evolving off the main sequence, the signature of the black hole's passage slowly erased by the changing dynamics of the galactic system. Or perhaps the wake will persist, a faint thread visible to future observers as a clue to an ancient event. Either way, the black hole will keep moving, its motion determined by the gravitational kick it received long ago, a consequence of forces and interactions that unfolded in the chaotic heart of a merging galaxy system. And that, perhaps, is the final lesson of the runaway black hole. That the universe is governed by laws, by physics, by the interplay of gravity and motion and energy, but also by chance, by the particular configurations and encounters that happen at particular times and places. The ejection of the black hole was not inevitable. It required a specific set of circumstances, a galaxy merger, multiple black holes in close proximity, the right speeds and angles and masses to produce a strong enough kick. Change any of those factors, and the outcome might have been different. The black hole might have settled at the centre of the merged system, might have formed a binary with another black hole and spiralled inward over millions of years, might have remained a fixed and stable heart for the new galaxy. But that is not what happened. Instead, it was flung outward, set on a trajectory that carried it through space, leaving a luminous trail in its wake. This interplay of law and chance, or of deterministic physics and contingent circumstance, is part of what makes the universe so endlessly fascinating. We can predict the general behaviour of systems, can calculate the probabilities of different outcomes, can understand the mechanisms by which things happen. But the specific details, which galaxy merges with which black holes get ejected and which remain, which trails of stars form and which do not, those depend on the particular history of each system, the unique sequence of events that unfolds over billions of years. The runaway black hole is a result of that history, a product of the cosmic owl's violent past, and it carries within it the memory of events we can only infer and imagine. So as you drift off to sleep, or as you step outside one more time to look up at the stars, let your mind wander to that distant system. Picture, if you can, the overlapping rings of the cosmic owl glowing faintly in the infrared, their arcs of young stars tracing the ripples of a collision that happened billions of years ago. Picture the long, straight streak of light, a thread of stars stretching across 200,000 light-years, each one a sun born in the compressed wake of a passing black hole. And picture the black hole itself, invisible but undeniably real, racing through the gas at nearly 1,000,000 miles per hour, creating a bow shock at its leading edge, writing a story in starlight that we are only now beginning to read. It is a story that speaks to the grandeur and strangeness of the universe, to the power of gravity to shape and reshape matter over cosmic time, to the rare and remarkable events that punctuate the otherwise steady evolution of galaxies. It is a story that confirms ideas imagined decades ago, that opens new avenues of research, that deepens our understanding of the cosmos in ways both practical and profound. But above all, it's a story that reminds us of the universe's quiet, ceaseless motion, the galaxies drifting through space, the stars being born and dying, the black holes wandering between worlds, all of it unfolding on scales that dwarf human comprehension, all of it happening now as you read these words, as you look up at the sky, as you close your eyes and imagine the vast dark distances and the glowing trails left behind by runaway hearts. The next story is about to begin. Please relax and enjoy.